Hey, how's it going, guys? It's Mr. Lee here. I just decided to do a quick little video talking about the two really common sensors that are used today in the automotive applications, I guess, in terms of for triggering, for basically your information gathering. I was telling you about basically what sends information to the ECU regarding your crankshaft position or your camshaft position. Anyway, the first thing I want to talk about is the what is known as the pickup coil. The pickup coil would be used in places such as your crankshaft or your distributor position that I showed you yesterday, even in lab. What a pickup coil is, it is a magnetic pulse generator, and what it is basically it's a two-wire input sensor. So this would be a trigger in terms of our primary circuit components. It consists of a permanent magnet. So in here it's just regular magnet, north and south pole magnet. Okay, and around it is just a wire. In this case, one end would come from the computer and the other end would go back to the computer. It just wraps around in a tightly wound coil and then it goes back. Okay, so the magnet in this situation, it's always emitting a magnetic field, right? The permanent magnet, there's always these lines of flux, as you would say. Mr. Jav will probably explain it in way better detail than myself. Anyhow, on the other side is your reluctor wheel or your trigger wheel. In the distributor, it would be the trigger wheel, and on your crankshaft, it could be like a reluctor, a bunch of teeth, usually on your crank pulley or on your flywheel. And what happens is, because this is made of metal, and these peaks here, I just decided to make them little triangles. When the distance between your trigger wheel and the end of this permanent magnet, it keeps changing, right? What happens is the closer it gets, the magnetic field intensifies, so it gets stronger. And then when the air gap, let's say when it goes to the low part of your trigger wheel, then the magnetic field weakens. This constant up and down of intensity of the magnetic field causes the magnetic fields to collapse into itself. We talked about it a little bit when we were talking about ignition coils, how through the process of induction, as that charged magnetic field collapses over your primary and secondary circuit, it creates a spark. Except now we're not dealing with the transformer. We're just, this field constantly just collapses back into itself, which will create an AC signal. So it's inducing a voltage in itself. The key thing you got to know about a magnetic pickup, this type of sensor, it does not need a power supply. It's just a wire that comes out of the ECU and goes back to the ECU. Okay, it's whenever there is motion, and that's the key. This sensor only works when there is motion. And remember, we were talking about the laws of like induction. You need if you have a conductor, if you have a moving magnetic field over the stationary conductor, it will induce a voltage, right? In this case, we have a moving this moving reluctor wheel will constantly manipulate the magnetic field, which is where your motion is coming from, will induce the voltage into this conductor, which is the wire here that goes back to your computer. Your ECU will use these waves. It'll monitor the frequency of these waves over a given amount of time to determine things such as engine RPM, and also usually in terms of crankshaft positioning. Let's say you have a 6-cylinder and you have 6 equally spaced teeth. They'll put an additional one as an interrupter, or basically that would be your signal to the computer to say, hey, that's cylinder number 1. Right, that's when cylinder number 1 is at top dead center. So that's how it would use it as a referencing signal. The disadvantage of this sensor, as I mentioned again, is it has to have motion. Right, it's only in effect if you have usually something spinning or something moving. Okay, I'll mention the ways you could test this. Basically, because it's just literally a coil around a magnet, you can think of, if you were to, let's say, bench test, meaning if you want to test this particular sensor without the engine running or stationary, you can do a quick resistance check, just like you would check a light bulb. Obviously, because it's a coil wound tightly, you're going to have a given resistance specification. I would look that up in Mitchell, and then you would just set your meter to ohms, and you would just see if there's the proper resistance. Obviously, if some part of the coil was shorted, then your resistance would be a lot lower than specified. Or obviously, if there's a break, if it was cut, then you would probably have an open. Right? In that case, your sensor, your magnetic pulse generator won't be working anymore. If you want to test it dynamically, let's say you ideally you want to use an oscilloscope. Obviously, you would same thing. Put it across these leads, and you'll be able to monitor this wave form here. If you use your voltmeter, and I'll attach another video that shows that you can still, you'll see the response in your voltmeter depending on how fast the signal is, but the voltage readings you're going to be getting are going to be meaningless because it's too much of a delay. Like you'll be able to detect the up and down, but you won't actually be able to detect how much it went up or how much it went down to the negative side, just because it's happening too quickly. All right, so that's basically the magnetic pulse generator. I would still refer to the notes to get more details on that. The second type of sensor that's really common to be used in the automotive field is what is known as the Hall effect sensor. Okay, the Hall effect sensor, the big difference is it's a 3-wire sensor versus a 2-wire sensor, and it's also a powered sensor. This can be used obviously in your distributor to monitor camshaft positioning. It's used sometimes even in the crankshaft as a crankshaft position sensor. And it's really useful as a position sensor as well. But before we get into what's going on here, we have to understand what is the Hall effect. I'm going to give you a really basic explanation, and you can see why this would be an advantage. Again, Mr. Javananian will give you the really in-depth, better explanation, but I hope this really helps. Okay, so first, let's just imagine this is my little drawing of, it's just a wire. All it is a wire. One end you have positive, and the other side is negative or ground or whatever. So we're gonna put a little magnifying glass here, and let's imagine the wire is like this tube here. Within this wire, you're gonna have little electrons, these negative electrons, flowing from positive to negative. So it's just like water, right, flowing through a tube. Okay, you follow me there, right? So what is the Hall effect? So let's just imagine now I take this wire, and this section here I'm gonna blow it up, make it just a little bit bigger, just for explanation purposes. We'll make it wider, right? Like, you know what I mean? I'm expanding it, right? So as electrons flow through the wire, right? If you were to take your multimeter and set it to volts, let's say, and you were to measure, let's say, one side of this wire and the other side of the wire, obviously we'll see 0 volts because, you know, there's no load, there's no potential difference. Electrons basically just are flowing through this wire. Okay, now where the Hall effect comes into play is now we're going to imagine, so let's say we instead of a wire, we attached to this wire a flat piece of conductive material. We'll use like a semiconductor, usually what they use, a semiconductor material. You have electrons flowing through the same way it did here. Now, let's say you take a permanent magnet, however, okay, this is what the Hall effect is. If you take a permanent magnet, and specifically having, say, the south pole on this end, because electrons leave the top, the magnetic field leaves the top of the magnet and will enter back in the south, so positive to negative. What happens is, now, when you bring the magnetic field close to this semiconductor plate, okay, where the electrons normally would just be, you know, they fill up, you know, even out the spaces and then kind of exit out the negative end. What happens is the magnetic field, as it gets closer to this semiconductive material, all the electrons, which were originally just mind their own business and going through, they get attracted by this magnetic field, basically. Okay, the electrons try to basically follow these lines of magnetism here and try to enter the magnet, and thus what happens is, if you were to visually draw this out, all your negatively charged electrons will end up on one side, and then what's left with is obviously your positive charge, right? And in this situation, if you were to take your voltmeter and measure again, say for volts, say positive, negative, and now you will actually see a potential difference. Because everything's separated, you're going to have a voltage reading. Now, how this applies to in terms of using it as a position sensor, or even as a signal for an on-off signal for your distributor, your crankshaft, is depending on how close or how intense the magnet is, that'll determine how many negative electrons go to the one side. So obviously, if it was really far away, we'll probably get a low voltage. If it's really close, maybe all of them will go to one side. So for example, when you do, this is going to be a 3-wire sensor, right? You're going to have voltage in, 5 volts, and then ground, and this is signal coming out, right? So for example, if this was used as a position sensor, like let's say a fuel level sensor, imagine now either your magnet is moving, or this let's say this either this or this was attached to your bobber in your fuel tank, let's say, right? As you fill up your fuel tank, the bobber gets closer, which means the magnet gets closer. Maybe that'll translate to, let's say, somewhere closer to 4.5 volts, right? Where you're running out of gas, the distance between your hull and your magnet gets farther away, then the potential difference ends up being a lot less. Let's say maybe 1 volt. You see what I'm saying? So the Hall effect is very useful because basically it could be measured static. Once your fuel level hits a certain point, you shut off your car, you turn it on again, it doesn't have to move, right? It's the computer will monitor the voltage difference, the potential difference in this Hall element, right? The magnetic field doesn't have to be in motion. Okay, now if I haven't completely confused you yet, if you go back now to, in terms of the distributor or in a crankshaft position, how we would use this type of sensor to create a signal. First off, I gotta mention to you, the signal that comes out of a Hall effect sensor is digital. It's just on and off. Okay, the computer looks at the on and off over a period of time, basically the frequency, right? First of all, the frequency data and the duration data is used by the computer to determine where the crankshaft is and also your engine RPM speeds. Okay, so going back to distributor. I remember, I think I showed you guys that old style distributor in lab where we opened it up on the inside, there was a permanent magnet, and on the other end there's a Hall element, and then the shutter wheel. Basically, it's literally just a wheel like this with a bunch of like slots into it. These slots basically interrupt the lines of force in this case. So what's going to happen is, just like I was explaining in the other drawing, here's your Hall element sensor, right? You got positive and negative, your electrons mind their own business, they're just kind of flowing through and then back to the computer, right? What happens is, though, let's say the shutter, there's an opening here, the shutter hasn't interrupted it yet, right? This magnetic field basically manipulates these electrons inside this Hall element, which will create a given voltage signal, right? Now, as this metal shutter, as it spins, as your distributor spins, if it gets close and it interrupts, let's say, between the Hall and then the magnet, the magnetic lines of force, they don't actually pass through and permeate and then and affect this Hall sensor. They will basically use the metal shutter wheel as a path and basically go back into the permanent magnet. So you will not have any influence on the electron flow in this situation. Like, your electrons will still continue to flow, and this will translate to, let's say, 0 volts, right? So this type of sensor, because it's just like on and off, on and off, on and off, what the manufacturers will do is they'll design these slots of different widths, right? So depending on the width and depending on the frequency, the computer will know exactly which cylinder's where and which cylinder's ready to fire. Okay, hopefully that makes a little bit of sense. We will talk about this a little bit more in class. And again, to diagnose this, to check this sensor, it's basically the same way as I taught you as you look at any other 3-wire sensor, right? You're going to make sure you have your feed, your ground is good, right? And then your signal. The signal is what's coming out of the sensor, remember, right? And in this case, to monitor this type of sensor, you would need to use an oscilloscope. An oscilloscope will actually display a graphical representation of what's happening with your crank or cam sensor output. All right? Hope this helps, and yeah. Thanks for listening.